Hey everyone, I hope you all are doing good. So in this lecture, we're going to be covering special graphs such as the complete graph, cyclic graph, and cubic graphs. So in the last lecture, we covered the terminology of graphs, right? And this one, we're just going to be covering the special graphs. Very easy lecture, and we will just quickly cover them all and then take a look at a few examples too, right? Okay, so complete graphs, Kn, it's represented by the word Kn. Kn is a simple graph of n vertices where each pair of vertices is directly connected. So the idea is very simple. Whatever the vertices you have, you just connect them all. It's a simple graph where the number of vertices, you just connect all of them together, right? So let's just take a look at a few examples. So let's say if you have a graph with just one vertex, you can't do anything, it's just you have A. K2, you just connect A and B together, so that's done. In K3, I connect B to A to B, and all these three are connected, right? Because it's an undirected graph. So I don't need those arrows once again. Okay, now take a look at A4 again. Now in A4, I've connected A to B, A to C, D to B, D to C. But I also need to do this cross over here, which is connect A to D and B to C as well. Right, so the idea is very simple. In each of these examples, if you look carefully, right, we're connecting every vertex to every other vertex that's available, right? So A is connected to BC, B is connected to AC, C is connected to AB. Same thing for this as well, and same thing for K2 and K1, right? Okay, let's take a look at the formulas. Let's very quickly. So the number of edges is equal to C, the combination n comma 2. Now, once again, if you don't know the combination formula, I would suggest you watch the permutations and combinations video. I've covered permutations and combinations in detail, right? Okay, so the idea is, um, let's first understand why is the number of edges is equal to C n comma 2, right? It is because each edge is equal to pick a pair of vertices. Now, if you remember, if you understand combinations, right, the entire idea is you have a certain number of vertices, and each edge is basically you just pick a pair, right? You just pick a pair of vertices. So if I have A, B, C, and D, at any single edge, I'm picking two of them, right? So I could pick A, C, B, D, I could pick C, D. But the idea is that they have to be, the order does not matter. So if I say I picked C, D, and DC again, that wouldn't count different, right? That would be the same thing. So since the order doesn't matter, we use the Cn comma 2 formula, right? And 2 over here represents because each edge you're picking two values. So from n, you're picking 2, okay? So the degree is equal to n minus 1 for every v. Now, why is the degree of every single vertex n minus 1? Let's try to understand this, right? Now, think about this. The idea in this graph is that whatever vertex you have, you connect it to every other vertex. But since it's a simple graph, you can't make a loop back to the graph itself, right? What I'm trying to say is that in this one, let's take a look at this example, right? I've connected A to B, A to D, and A to C, but I cannot have a loop around A because this is a simple graph once again, right? And that's why every single element has a degree n minus 1 because you cannot connect it to itself. So I've given the explanation as well. Each vertex connected to every other vertex and not itself, right? If we had loops, then we can say that every vertex would have degree n. Okay, so I hope you were able to understand this example. Now let's just quickly solve this K4 example and show you that how these formulas work, right? So if you look at the number of edges, I have number of edges equals Cn comma 2. So let's just count it ourselves, right? If you look at this, this would be 4 plus 2, which is 6 edges. And if you solve C 4 comma 2, this is also 6. So that means we are correct, right? Let's take a look at the degree of each one. So A has the degree 3, C has the degree 3, D has degree 3, and B has degree 3 as well, right? So first of all of them have the same degree, and secondly, the degree is n minus 1, which is 4 minus 1, which is equal to 3. So both our conditions are satisfied, right? And you can try doing this for these K1, K2, K3 as well. Now, once again, why are these formulas important? Because we can do this manually for very small graphs, but once again, if we have bigger graphs, let's say K10 or K20, or if we have some sort of exam question, in that case, we would need to know these formulas, right? Okay, now let's understand the cyclic graphs. Okay, Now let's understand the cycle graphs, right? Once again, a very simple concept to understand. Cn is equal to the n vertices arranged in a loop. Each vertex connects to the next one, and the last one connects back to the first. I think this is a very easy concept to understand. The idea is very simple. It's pretty much that you're making a loop, right? Whatever vertices you have, you just keep on connecting them, and you connect the last one back to the first one, right? So I think it's just best to explain it with examples. So you have C3 over here, which is, for example, if you look at this one, right, you have A, B, C. So you connect A to B, B to C, and C back to A, right? It makes a triangle. You look at C4, A to B, B to D, and D to C, and C to A, back again. So it's pretty much making a loop. If you look at it, right, if you read the definition, n vertices arranged in a loop, each vertex connects to the next one, and the last one connects back, right? So over here, A connects to B, B connects to D, D to C, and C connects back to the first one. So same way with the pentagon and the hexagon as well. You can just take a look at them. Okay, so that's just the basic definition, very easy to understand. Let's take a look at the formulas now, right? So in a cycle graph, the number of edges is equal to n, which is basically the number of vertices, right? So the number of edges is equal to the number of vertices. And the degree is 2 for every vertex. Now, why is this happening? So once again, let me just quickly explain these formulas. Y n edges, each vertex contributes one next edge in the loop. So let's just quickly take a look at this, right? In C5, you have 5 vertices, right? So it's saying each vertex contributes one next edge in the loop. So let's consider A contributes 1, right? E contributes 2nd, D contributes 3rd, C contributes 4th, and B contributes the final one, right? Same thing for the pentagon. A contributes 1, F contributes 2nd, E 3rd, D 4th, C 5th, and B 6th. You can also go the other way around, but that doesn't really matter. The idea is simple. You kind of consider that one vertex is contributing one edge in a way, right? And that's why the count of the number of edges is basically n. Okay. Second point is the degree is 2 for every single vertex. Now, the reason is very simple for this one, because every single vertex is connected to one next one and one previous one, right? So A is connected to B. So let's say if you're going in this direction, right, then your next one would be B and your previous one would be C. If we reach B, then previous to B was A and B's next value is C, right? So it's pretty much that in a loop, each vertex has only 2 neighbors. So every single one, if you look at any of these examples, every single vertex in any of these examples just has 2 neighbors, right? Okay, so I hope you were able to understand. Let me quickly explain one more concept. So C3 is also equal to K3 as well, right? And the reason is very simple, because in K3, it's a complete graph, right? Triangle is also a complete graph. Every single vertex is connected to every other vertex, right? So triangle is also a cycle graph and also a complete graph. This is just a very basic concept that you should keep in your mind. But if you go from C4, C4 is not equal to K4, right? Because we have not connected AD and we have not connected BC as well, right? So I hope you were able to understand. Now let's move on to the next topic. Okay, everyone. Now let's understand hypercubes, right? This is going to be a bit tricky to understand, but it wouldn't be too bad. So let's start with understanding what are hypercubes. The idea is that instead of just A, B, C, D, and whatever, you're using the bits now, right? So vertices are basically all binary strings of length n. Okay, so let's think about this, right? I've just given these examples, so let me just explain each of these examples. So think about 1-bit graph. In 1 bit, you can only have 0 or 1. So the only possibilities are 0, 1. So let's just have 0, 1 and connect them together. Okay. Edges is connect to strings that differ exactly in 1 bit. Now, this is a very important and confusing to understand. Now, differ by 1 bit basically means that let's say if you have something like 0, 0, 0, 1, right? Differ by 1 bit would mean if you just change one of these bits. So I can change this one to 0, right? Or what I can do is I can change this 0 over here to 1. But the problem is that I can only change 1 bit, right? If I change, let's say that I had 0, 0, 0, and if I change 2 of these bits, this is over here I've changed 2 bits, right, instead of 1. So this says edge is connect to strings that differ only exactly in one bit, right? Very important to understand. So let's take a look at the examples. So if you look at Q1, in Q1 we have just 0 and 1. So 1 could be only 0 and 1 bit, right? And if you look at it, if you flip 0 by only 1 bit, it would result in a 1. And that's why both of them are connected, right? So if you flip 0, it results in a 1. If you flip 1, it results in a 0. Okay, let's take a look at Q2. Now, these are all the possible 2-bit strings, right? 2-digit bit strings, I should say, 0, 0, 0, 1, 1, 0, 1, 1. And look at the connections carefully, right? 0, 0 is connected to 0, 1 and 1, 0 because they differ by only 1 bit, right? So if you just change this digit to 1, it results in 1, 0. And if you change this, the first 0 on the right side to 1, it results in 0, 1. Okay? And 1, 0 and 0, 1 are connected to 1, 1 because if you change one of their bits, it results in 1, 1, right? Now, one important thing to notice is 0, 0 is not connected to 1, 1, right? Why? Because I need to change 2 bits of it to result in a 1, 1. And we only connect an edge where they differ in exactly 1 bit, right? So very important to understand. Okay, so I've given this another example over here, a bit more tricky to understand, but these are all the 3-bit strings, right? Which have the length 3. So 0, 0, 0, 1, 0, 0, 1, 0, 1, they're all connected. And I want you guys to try to pause the video and take a look at this, right? In each of these connections, the edges are the places where they differ by only 1 bit. So one of the examples is if you take a look at this one, right? They only differ by 1 bit. So 0, 0, 0, if you change the first 0 and change it to 1, that's why they're connected, right? So that results in 1 change. Okay, same way 0, 0, 0 is connected to 0, 1, 0. But if you find out where we have not connected anywhere where you're changing more than 1 bit. Okay, so let's take a look at the formulas now. The number of vertices is equal to 2n. Let's understand why is the number of vertices 2n, right? Okay, a binary string of length n has 2 choices for each bit. Okay, so the idea is very simple, right? If you know bits, the bits only possible are 0 or 1, right? So if you have 1 bit, if you are making a graph of the Q1, only 0 and 1 bit are possible, right? If you think about Q2, at each position, I can have either 0 or 1, right? 0 or 1. So that's why it's pretty much that what you do is you keep on multiplying by the value of 2 and you keep on doing this. So whatever the n value is, each position can hold 0 or 1. And that's why you have 2 multiplied by, or I should say 2 to the power of n available options, which is 2 to the power of n vertices, right? So if you can also verify from this, so 2 to the power of 1, 2, that's why Q1 has 2 vertices, right? Q2 has 2 to the power of 2, which is 4. Q3 has 2 to the power of 3, which is 8. So you have 1, 2, 3, 4, 5, 6, 7, 8. Okay. So once again, why? Because every single position, every single possible bit you can have is, it could either at one position you could have 0 or you could have 1. So that means 2 multiplied by 2 multiplied by, keep going on until you have a n-digit bit string, which results in 2 to the power of n. Okay. So second one is, I'm sorry if this is a bit more like clustered. I didn't have much space left, so that's why it's kind of like messy, but I hope you're able to understand what I'm saying, right? Okay, so why the degree is n? Let's understand the degree, right? So it says degree v is n for every single v. Okay, for any string, you can flip one of the n bits to get the neighbor. Let's try to quickly understand what this means, right? Okay, think about this example. Let's just take this bit, right? You can flip it 2 times. I can either flip to 1, 0, or I can flip it to 0, 1, which means I can flip it 2 times, right? That means it would have 2 neighbors. Okay, so take a look at this, right? 0, 0, you flip 1, you can flip it 0, 1, or you can flip it to 1, 0, right? So it has 2 neighbors. It says the degree is n for every single v, because the idea is for any digit of whatever the bit string is, right? So this is a 4-digit bit string. I can flip this 0, I can flip this one, I can flip this one, I can flip this one. And each one would result in a different neighbor, right? That would give me 4 total neighbors, which would be n in total. So once again, let's take a look at this example. Take a look at the neighbors of 0, 0, 0, right? 0, 0 is connected to 1, 0, 0, that's 1, right? It's also connected to 0, 1, 0, that's 2. And it's also connected to this over here, 1, 0, 0, 1. So that's 3 in total. And same thing for each of these values, right? And because the idea is very simple, once again, whatever bit string you have, if you just flip all of its digits once, it results in a different bit, and it results in its neighbor. And that's why the total over here results in n. Okay. Final one. Now the edges are basically equal to n multiplied by 2 to the power of n minus 1. Okay, let's just quickly try to understand this one, right? Okay, I'm going to erase this point, so just to explain it. Okay, so we are saying why are edge equal n multiplied by 2 to the power of n minus 1? Because the sum of the degree is equal to 2 multiplied by the number of edges. Okay, let's take a look at this formula, right? We're saying the sum of degree is equal to 2 multiplied by the number of edges. Okay, so this means that the sum of degrees divided by 2 is equal to the number of edges. Okay, let's find the degree, right? We have been given the number of vertices is 2n, and the degree of every single node, or I should say vertex, is basically n. So that means the sum of the degree would be 2 multiplied by n, 2 to the power of n multiplied by n, right? That's the exact thing. And since the number of edges is equal to the sum of degrees divided by 2, I can divide it by 2 and I get, okay. So sum of degrees is equal to 2 to the power of n multiplied by n. I hope this makes sense because this is the number of vertices, right? Vertices, and this is the number of, I should say, degree of each, right? So, and if you want to find the edges, E is equal to sum of degree by 2, which is equal to 2n multiplied by n by 2. And all you can do is, if you just reduce this, you get 2 to the power of n minus 1 multiplied by n. And that's your final answer. Right, so I'm sorry if it's kind of getting messy on the board, but I hope you were able to understand. Once again, I'll just try to quickly explain hypercubes again. In a hypercube, all bit strings, vertices are all bit strings of length n. Basically, you represent every single vertex by a bit string, right? So let's say if you're talking about one bit string, it would be 0, 1. 2, it would be 0, 0, 0, 1, 1, 0, 1, 1. And you connect the neighbors only if they differ by 1 bit, exactly 1 bit, right? So you can see in these examples. The formulas are also pretty logical to understand. You can remember them, but I think it's also important that you understand why exactly we have these formulas. So number of vertices is equal to 2n because every single position you could have either 0 or a 1. That's why it results in 2 to the power of n. Edges is equal to n multiplied by n 2 to the power of n minus 1 because of this formula that we know from the previous lecture. And the third one is the degree is equal to n. And n, why? Because for every single bit string that you have, whatever the length is, you can replace, or you can, I should say, change one of its bits and it would result in its neighbor, right? So in this bit over here, I can change it 4 times because I can change 4 of these bits and it would result in 4 of its neighbors. That's why for every single node you have, their degree is basically n, right? So that's pretty much it for this lecture. I hope you were able to understand everything that we covered, and I'll see you guys in the next video.